Well, here's another fairly simple experiment using a basic DC circuit. Let me pick up where we left off in our last experiment in trying to verify Ohm's law. So we put two resistors in series with each other, R1 and R2, and an ammeter in series also with those resistors and the battery. And then there was a voltmeter placed in parallel with R2. So we were trying to see how changing the current through resistor number 2 affected the voltage across resistor number 2. Now, that should just follow Ohm's law, which expresses a linear relationship. So the decade box was really a sneaky way in controlling the amount of current in the circuit. With less resistance in the decade box, more current went through the circuit, meaning more current went through resistor number 2. So when we graphed the voltage through resistor number 2, as its current increased, we just had a linear relationship between voltage and current as expressed by Ohm's law. The slope of this graph is nothing more than the value of the fixed resistor. Here we're going to do something different. Instead of connecting the voltmeter across the resistor, we're going to put a battery and an ammeter and a resistor all in series with each other. But this time the voltmeter is going to be connected across the battery. Now in this diagram, we also see a second resistor, but that represents the internal resistance to the battery. See, when a battery is hooked up in an electrical circuit, if you connect this and run a current and come back and pick up any of these batteries, they feel warm because the current has to go through the battery itself, and the battery is not without resistance. Now, I'm not saying that if you get a hacksaw and cut this open, you're going to be able to find the resistor they put in there. That's not the idea of internal resistance. There's no additional intentional resistance put in here. It's just, it is a path for the flow of electricity that's not perfect. There is resistance to a battery. So, what happens is the greater the current in the circuit, then the greater the internal voltage loss of the battery, and so the voltage across its terminals actually becomes less and less the greater current it provides to the external part of the circuit. Anyway, the decade box now is our only external resistance in the circuit, and I need to go from the positive terminal of my battery to either one of the inputs of the decade box, go from the negative terminal to the other input, and then if I close this switch, my circuit's complete, but I'm not reading anything. So as always, an ammeter should be connected in series. So I'm just going to make one series loop that includes a battery, an ammeter, and the decade box. So take this multimeter, dial it to the milliamp setting, disconnect here, okay. Now this time, the voltmeter is not going to be used to verify Ohm's law across some external resistor. What we're trying to use with the voltmeter is show that the voltage across the terminals of the batteries drops the greater the amount of current that flows in the circuit. So instead of getting this result, the hypothesis if we graph VT, the voltage across the terminals of the battery on the y-axis, and we graph current along the x-axis, we're not going to see Ohm's law. We're going to see that with greater and greater current, there's less and less voltage across the terminals of the battery. So this is the expected outcome. Now, what's the meaning of this y-intercept? That represents the greatest possible voltage that the battery could provide. We refer to that as the EMF of the battery, the ideal voltage. The slope of this graph, well, we'll come back to that at the end of the investigation. So all we're going to do is start with 115 ohms of resistance in the decade box and gradually reduce it from 115 to 95 to 75 and so on, all the way down to 11 ohms. And record current, record voltage, and see what we get. So, back to the voltmeter. It's being connected in parallel with the battery. So I can just piggyback that into the high potential and that one into the low potential, and the voltmeter is going to be measuring the voltage across the terminals. Now it reads 0 at this point. Because the circuit's not quite complete yet, I've got to close this switch, but I have to be very careful in this experiment. There's no second value of fixed resistor to add any resistance in the circuit. Remember, these ammeters have a very low internal resistance. So if the decade box doesn't have any resistance in it, there's a chance that there'll be too large of a current and we could damage the ammeter. So before closing the switch, I'm going to make sure this is set to the initial value of 115 ohms. So I have to go to 1 in the hundreds place, 1 in the tens place, and 5 in the ones place, 115. Now I feel safe to complete the circuit. And we've got 23.65 milliamps, and the voltage across the terminals of our battery is 2.988. Now we're going to decrease the decade box from 115 to 95. 95, okay. So now the voltage across the terminals has gone down a little bit. Now it's 2.974 volts as the voltage provided across the terminals of the battery. And the current through the circuit is 28.03 milliamps. We go down to 75. As the current grows, becomes 34.32 milliamps. The terminal voltage becomes a little bit less yet again, 2.954 volts. Go to 55. Current's now 43.9 milliamps. Voltage across the terminals of the battery, 2.924. Down to 35. 61.6 milliamps, 2.873 volts. Down to 15. 104.1 milliamps, 2.76, it's trying to make up its mind. We'll call it 2.764 volts. Okay, then we're just going down one at a time from 15 to 14. 14 ohms of resistance in the decade box, 108.3 milliamps, 2.758 volts. Down to 13 ohms of resistance, 112.3 milliamps, 2.75 volts. 12 ohms of resistance, 116.8 milliamps, 2.740 volts. And our last data point, 11 ohms of resistance, 121.5 milliamps, 2.729 volts. Well, hopefully, like I say, when you plot that data, you get this result. Well, the governing theory here says that the voltage across the terminals should be equal to the ideal voltage minus what we call the internal voltage drop of the battery. The terminal voltage is the ideal voltage minus the internal voltage drop, which is this part is an expression of Ohm's law. The current through the battery times the resistance of the battery is the voltage loss from the battery. Ideally, it's a 3-volt battery, but it loses a little bit of voltage due to its internal resistance, so the voltage across its terminals is something less than the EMF. Now I can write this so it looks more like Y equals mx plus b. we can say the voltage across the terminals, which is being graphed on the y-axis, is equal to negative R times I is graphed on the x-axis, plus EMF. So this is y equals slope times the quantity on the x-axis plus y-intercept. And indeed, we have a y-intercept that should be the EMF. So what's the slope of this graph? It's the negative of the internal resistance of the battery. That's it.